At RubyKaigi last year, one of my colleagues, Maxime, gave a talk about her work on YJIT. It was at the time a brand new JIT. She's now given another talk this year about it. But in last year's talk, she spoke for part of her talk about this technique called object shapes and how it might be able to help out the JIT even more. Also at last year's RubyKaigi, one of my other colleagues at Shopify, Chris Seaton, gave a keynote address which he called the future shape of Ruby objects. He talked as well about object shapes, which Truffle Ruby, which he works on, actually uses. And he, too, spoke about how it could be useful in CRuby. And when I joined Shopify and was looking for something to work on, Maxime encouraged me to pursue this idea of object shapes. So out of those two talks comes my talk today about implementing object shapes in CRuby. And actually, I had to change this slide after yesterday because another one of my colleagues gave a talk, Coco Boone, called Towards Ruby 4 JIT, where he also mentioned object shapes quite a few times, again, talking about how they could be really beneficial for JITs. And so today, we're going to discuss this project I've been working on, actually implementing object shapes in CRuby, and I've been working on it alongside Aaron Patterson. We'll answer three main questions here. First, we'll discuss what are object shapes. Then we'll look at how they're actually implemented, what our implementation details are. And lastly, we'll talk about why MRI should adopt object shapes. So first, what are object shapes? Well, you might be thinking about a diamond maybe, or a triangle, or an oval. But this is not what we mean. We don't mean literal shapes. So what do we mean when we say object shapes? Well, the object part is really a Ruby object. So it's something like this object.new. And the shapes part, it's in quotations. It's just a metaphor or a symbol for this concept, this technique called object shapes. And with this technique, each Ruby object has a shape, and the shape represents an object's properties. Well, you might be asking, what's an example of a property? And something could be a frozen status of an object. So is it frozen or not? Or another thing might be its instance variables. So what instance variables does the object have on it? But let's look at some concrete examples of object shapes with concrete code. So in this example class, if we create an instance of example class, this instance will have a shape. And again, the circle here has nothing to do with actual circles. The shape will have on it instance variable names. So for instance, in this case, it will have instance variable A and instance variable B. And the shape will also have a frozen status. So if we froze this object, if we call e.freeze, it will be a frozen shape. And lastly, shapes also have IDs as a way to uniquely identify them. OK, let's look at another example. What if we have this example called completely different class? And we have an instance of completely different class. The instance variables on this shape are going to be C and D, as we can see here. And it will also have its own ID, or its own unique identifier. What if we also have a class called coincidentally same ivars? And we have an instance of this class, coincidentally same ivars. As you can probably tell by now, its shape will have ivars C and D. But these two shapes have the same properties. They have the exact same ivars and the exact same frozen status. So they're actually the same shape. This is a critical point. These two objects, these two instances, have different classes, but they have the same shape. Another thing to note is that the shape of an object transitions with new properties. So the shape of an object can change and changes whenever we add a new property. Every object starts at the root shape, which is an empty shape. So it has ID 0 and no ivars. It's our empty and base shape. And then if we set e to example class.new, as we run through the initialize method, its shape will change. So first, when we set the instance variable A, its shape will transition through an edge with instance variable A to a new shape, which just has the instance variable A and a new ID. If we set the instance variable b, the shape will transition again to a new shape. Now it'll have ivars a and b, and it'll have the next ID. It's also important to note here that, say, instead of setting both a and b within the initialize method, we had the initialize method which just set the instance variable a, and then this descriptive method that sets b. If we had our e, which we've already looked at, and we had an e2, which is another instance of the same class, and we called e2.setB, e2 would have this last shape because it has instance variables a and b, whereas e would have the middle shape here with ID 1 because it just has instance variables b. Just has the instance variable a. So this is a critical point as well. These two instances are instances of the same class, but they have different shapes. OK, so back to our initial example. If we now had another class, similar class, and we had two instance variables in here, a and c, let's take a look at what the transitions will look like, because they'll be similar to example class, but not exactly the same. So for this instance S, it'll start, like all objects, at the root shape. When we first set A, it'll make that same transition. And then there's no existing transition for C. So it'll create a new transition to a new shape whose ivars are going to be A and C with a new ID, and it will transition. And you might have noticed here the shapes form a tree. So if we actually ran all of the snippets of code we've accumulated to date through Ruby and generated the shape tree, it would look something like this. And we'll get more into the details here as we keep going. Now, we said earlier a shape of an object transitions with new properties. And we said one of those properties was a frozen status. So let's take a look at an example of transitioning with a frozen status. If we have this class where we only set A, as you know by now, we'll start at the root shape. We'll transition when we set A to the shape with ID 1 and ivar A. But then if we called a.freeze, we would make another transition, except instead of this being through an ivar, it would be through the frozen property. So we'll have an edge that's frozen, and we'll transition to a new shape. The ivar is only A, but frozen is true, and we'll make that transition. And another thing to note is we could also transition with other properties, and we'll discuss this a little more. So right now we transition with instance variables and frozen, but we could transition with even more properties. OK, so now that we've discussed what object shapes are, let's talk about our implementation, the thing we've been working on. So at its core is this RB_shape struct, which is 40 bytes, so it fits exactly in an R value, which we'll see will become important in a moment. And within this RB_shape struct, we have flags. And on the flags, we set the shape ID. So if we look again at our shape tree, we can see examples of shape IDs here. One shape with ID 0, one shape with ID 10. On 64-bit machines, we use 32 flag bits for shape IDs. This gives us 4.2 billion potential shapes. On 32-bit machines, we use 16 flag bits for shape IDs, which gives us 65,000 potential shapes. And just to contextualize those numbers, on Rails bench, we have at maximum about 10,000 shapes. And we also ran this on Shopify's monolith test suite, and there we had about 40,000 shapes at maximum. So even 16 bits would be enough, but 32 bits with 4.2 billion shapes is more than enough. We also encode the frozen status within the flags. So if you look at this shape tree, the shapes that are highlighted in blue are frozen shapes. And like we know by now, this means they've had frozen transitions. And another thing to note about these frozen shapes is that they're leaf nodes, right? Because we're only setting frozen properties and instance variables as transitions, once a shape is frozen, it can't then add any more instance variables, so it'll have no more transitions. Another thing to note is we have a pointer to the parent. So on a shape, it points up to its parent, and we'll see how this helps us traverse up the tree. And we have a pointer down to edges. So it's an ID table from ivars to next shapes. And this allows us to see, like we saw earlier when we make transitions, to see if there's already a shape with that transition. We also have the edge name, which we use to transition from parent to a shape. So for instance, this edge name is B here, and we use it to transition from shape to ID with ID 6 to shape with ID 7. And lastly, we have the IV count, and we'll see in a moment where this helps us out. This is the number of ivars currently on a shape. So you can see here the IV count is 1 on this frozen shape, and it's 2 on this other shape. And we allocate our shape list on the VM. So we have shapes, and as we create them, we fill them up on the VM. This has a memory increase of about 500 kilobytes on average, which on an empty Ruby script with nothing in it is less than 1% memory increase. You can imagine on a bigger Ruby program, it's significantly less than 1% memory increase. And we also GC shapes to further save memory. So if shapes aren't being used, we'll garbage collect them, and we'll reuse the shape IDs. And shapes mark their parents up the tree when they're marked. So we saw earlier, shapes have a pointer to the parent, and they can use this pointer to traverse up the tree and mark their parent in the marking phase of garbage collection. So next, let's talk about the critical point here. Why should MRI adopt object shapes? And there are 4 areas we're going to discuss. First, increased cache hits. Then decreased code complexity. Then we'll talk about how it's beneficial for JITs, why Kokobun and Maxime both have highlighted it. And lastly, we'll talk about performance. So increased cache hits. With shapes, we've changed how caching works on instance variable reads and writes. But in order to go into the details of this change, we have to first talk about how it works today. So if we go back to our example class and create an instance of our example class, where are the instance variables actually being stored? Well, it turns out today, E has an instance variable array. And the values of each of E's instance variables are going to be stored in this array. But you might be asking, what index are we storing them at? How do we know that? And we actually have per class right now in Ruby a map from instance variable names to their indexes in this array. So the way this will work to step through it is when we set A, we'll look for A within that map. It's not there, so we'll put it there at the next available index. And then at our index in the instance variable array, at the index 0, we'll set our value, the string A. And we'll do the same for B. We'll look for the ivar B in our instance variable names map. It's not there, we'll put it in at the next available index. And then at that index in our array, we'll put in the string value B, the value of the instance variable for E specifically. But you might be thinking hash lookup isn't cheap, right? It's not extremely expensive, but it's definitely not cheap to keep looking up these instance variables in this example class instance variable names array. So what Ruby does today is it caches this instance variable index lookup, and it uses the class as the cache key. So for instance, when we're setting the instance variable A to the string A, we cache, for example class, the index of A is 0. And then we do the same for B. For example class, the index of B is 1. This works great in many cases. But what about this case where we have class inherited, which just inherits from example class and does nothing else? And we have an instance of inherited.new. Well, inherited is going to be a cache miss with example class. It won't hit. So it's a cache miss even though it's running the exact same initialize method that we already have the cached instance variable name to index lookup for. With object shapes, this works slightly differently. So the first thing is that we no longer have this example class instance variable names map. We don't have it for any classes, -1, yet index 0. The index is going to be the IV count -1, yet index 0. The index is going to be the IV count -1, 0. The index is going to be the IV count minus 1. And the other thing to note here is instead of using class for cache key, we use the shape ID transition. So let's walk through an example. If we're setting the instance variable a to the value of the string a, we start at shape 0 at our root shape. We transition through the instance variable a to a shape with ID 6, and IV count is 1 here. So index is 0. So we can say the shape transition from shape 0 to shape 6 has index 0. Let's look at the same for B. We're going to start at shape with ID 6. We'll transition through the instance variable B to shape with ID 7. And the IV count here is 2, so the index is going to be 1. And we can say shape 6 transitions to shape 7 with index 1. Now, if we look at our inherited class here, and you might know where this is going, it'll have the same shape transitions because the cache is no longer class dependent, which means we'll have cache hits in this case. So shapes, the first thing we want to talk about is shapes had increased cache hits. Another thing we can discuss is decreased code complexity. So we just saw an example of that where we were able to remove the instance variable index name completely. When he gave his keynote last year, Chris Seaton talked about the questions that Ruby master has to ask today when setting instance variables. And he talked about all sorts of different questions. Just to name a few, we have to ask, is the object frozen? What's its type? What's its class? Does the class match? Does the class serial match? And so on. And we're not going to discuss each one of these, but object shapes has fewer checks than this. Specifically, let's look at the question, is the object frozen, and how that changes on the fast path with object shapes. So we'll see a reduction of frozen checks in instance variable sets. Before object shapes, let's look at what set instance variable looked like. Now this is pseudocode because I didn't want to throw a bunch of C up on the screen. The parameters that set instance variable takes are an object to set the instance variable on, a cache, like we've already discussed, an IV name on which to set the value, and a value. And the first thing we have to do is raise a frozen error if the object is frozen. And we've discussed this already, right? We can't set an instance variable on a frozen object, so we have to check that every time. Then we have our caching check. So again, we use the class for the cache, so we check if it's a cache hit or a cache miss. If it's a cache miss, we have to do our expensive computation to find the index. And remember, that's what we looked at here, where we're saying the hash lookup isn't that cheap. Once we've done this computation and we found the new index, we can then set the instance variable, set the appropriate instance variable on the object to the value. So this is what it looked like before object shapes. With object shapes, the first thing we'll notice we can change is this caching mechanism. We're no longer using class, we're using shape IDs, as we've discussed. And we know our expensive computation looks slightly differently now. We know that it's going through this shape tree. So say we were starting at this shape with ID 7, that was the shape of the object, and we were looking for this, say we were looking for the index of A. We would traverse up the shape tree once, we would traverse one more time, we would see, okay, here's the IVAR A, let's get the IV count. We know index is IV count minus 1, that's our index. But what you might have noticed here is that the frozen status is encoded within the shape ID, right? The shape ID is already telling us the frozen status, so we only need to check this on the slow path. And let's take a moment to process this. If an object, because the shape is saying whether the object is frozen or not, we know that if an object with that same shape has already set an instance variable, then that object is necessarily not frozen. So we know an object with the same shape can also set an instance variable. Another way to think about this is if we couldn't make this transition, we would have already seen a frozen error since we had a cache hit. So we move the frozen error into our slow path, and our fast paths just becomes setting the value on the appropriate instance variable. The next thing I want to discuss is how object shapes is beneficial for JITs, to echo what both Kokobun and Maxime have already discussed. Before we get into that, we need to understand this concept of embedded versus extended. So what does it mean when people say an object is embedded versus extended? As quite a few folks have discussed already in RubyKaigi, we have our Ruby heap is our main Ruby memory, and we have an OS heap, which has secondary memory available to us. And obviously not to scale, but we have objects that we store on our Ruby heap. And in many cases, we can store the instance variables right within those objects. But what happens if we have more instance variables than we have space in the object for? Well, then they go to our OS heap, and we have a pointer from our object over to where they are on the OS heap. If the instance variables fit within the object is called embedded. And if they don't fit within the object, if we're storing them externally, it's called extended. OK, so now let's look at some YJIT-generated assembly code with object shapes. So we're going to look specifically at instance variable get. Without object shapes, it looks something like this. No need to read through it yet. We'll get to it. With object shapes, it looks something like this. The code in the light gray here is the same for both of them, so we'll remove it. OK, so now this is the core difference here. And the first thing you might notice is that there are fewer total instructions with object shapes. In assembly code, fewer instructions is a good thing. Specifically, there are 2 fewer total instructions. Another thing you might have noticed is that without object shapes, we need to do 3 separate checks. Each check is expensive. So first, we need to check the class. Then we need to check the class serial, which is saying, in case the class was garbage collected, we're really making sure this is the right one. And last, we want to check the embedded status. This is what we just discussed. So if an object is embedded versus extended, its instance variables are going to be in different locations. So it's important for the JIT to know that and guard against it. With object shapes, we mask the shape, the embedded, and the type all in one mask, which gives us just one check that we have to do in this JITted code. We check the shape, the embedded, and the type all in one comparison. And like we were saying earlier, we could eventually even put embedded and type in the shape. So remember, we were saying we could transition with other properties too. We could make that check even simpler. Another thing you might see here is there are 3 memory reads without object shapes. Memory reads are significantly more expensive than register accesses. I think 2 orders of magnitude more expensive. And with object shapes, we only have 1 memory read. So overall, with object shapes, this assembly code generated by YJIT has fewer instructions, fewer comparisons, and fewer memory reads. The last reason to adopt object shapes that I wanted to discuss was performance. So like we've already talked about, we have increased cache hits. And let's look at some performance metrics here. So if we look at micro benchmarks, these micro benchmarks represent object shapes divided by master. So any number greater than 1 means shapes is faster. Any number that's exactly 1 means they're the same speed. And any number less than 1 means that master is faster. So these ones are all within 2%, and micro benchmarks have quite high variance. So within 2% is roughly the same speed on micro benchmarks. We have 3 cases where shapes is faster. You'll notice we had none where shapes is slower. And we have 2 micro benchmarks in Ruby where shapes is significantly faster. Now, the one I wanted to point to specifically is this top one, this VM IVAR init subclass, where shapes is more than twice as fast. This is what the benchmark itself looks like. And the way Ruby benchmarks works, the part that's being repeated, that's being actually benchmarked over and over again, is this B set IVARs, C set IVARs, back to back to back. And if you'll notice here, B and C have different classes that both inherit from A. So they both call the same method, but they're different classes. And this is exactly the case we talked about already, where with the way Ruby is today, we have cache misses on this case, but with the way it would be with shapes, we have cache hits. And so you can see it more than doubles the speed in this specific case. The next performance benchmark I wanted to highlight was Rails Bench. These numbers are all in requests per second, so higher numbers are better. It means we can do more requests per second. And I measured over 10 runs and took the average. And you can see these are the averages. Shapes is higher. Shapes is actually, the Shapes branch here is about 2% faster on Rails Bench over 10 runs. And so next steps, what's the current status of this project? What are we planning to do next? We put up an issue a few months ago when we were at the beginning phase of work on this project. And we're now at a point where we think Shapes is good enough to merge. We'll write an update as soon as I return from this trip with these latest numbers and the latest information, as I've just discussed, and are hoping it can be upstreamed. If you're interested in following along with the bug, here's a link to the Redmine issue itself. Thank you so much for having me at RubyKaigi and for listening to this talk.